Welcome back. Today we're going to start section 5.6 of Edwards' Penny, which is about matrix exponentials. And as a warm-up exercise, how many of these power series can you remember? So these are the Taylor series for e to the t, cos t, sine t, and hyperbolic cosine and hyperbolic sine, which maybe we haven't mentioned before in this class. Okay, so I can remember all of them. We know that e to the t is 1 plus t plus t squared over 2 factorial, t cubed over 3 factorial. The general term is t to the n over n factorial. And using, related to Euler's formula, we already recalled that cosine t, being an even function, only has even powers. And they go in an alternating way, so it's 1 minus t squared over 2 factorial plus t to the 4th over 4 factorial. And in general, if it's a t to the 2n over 2n factorial, then the alternating sign can be written as minus 1 to the n, just checking it for t to the 0 and t squared. And sine t, being an odd function, only has odd powers, and they alternate as well. And you could write down the general term. Hyperbolic cosine is 1/2 e to the t plus e to the minus t. And if you go stare at the e to the t power series, you'll see that this process cancels out all of the odd powers, and the even powers are all the same, so that when you divide by 2, you get something that looks like cosine, except all the signs are plus. And for hyperbolic sine or sinh, when you take e to the t minus e to the minus t, all of the even powers in the exponential expansions cancel, and the odd ones add. So when you divide by 2, you get what looks like the sine of t series, except all the coefficients are positive. These expansions will be relevant in one of your homework problems for this week. And actually, when you compare cosh and cos, notice that if you just take cosine of it, using the power series to define it, then since it quantity squared is minus t squared, and so on, you'll notice that cosine of it is actually the same as cosh of t. These are actually the same functions if you think of complex inputs just evaluated at rotated points in the complex plane. And similarly, if you take sine of it, then it'll start out as it, and then it'll be minus I cubed t cubed over 3 factorial which is plus I t cubed over 3 factorial. This will be I times the sinh of t. All right, so there's lots of reasons why cosine and cosh and sine and sinh have similar properties. It's because they're actually essentially the same functions. All right, so we'll see in a second, but this warm-up exercise has to do with matrix exponentials. And so if A is a square matrix, we're talking about e to the a, or e to the ta, where that's a function of t. This is, matrix exponentials come up in a lot of places in pure and applied math. Wikipedia is always the first place to go if you see something new and interesting. And what we're going to do today and in the next lecture is, well, we'll talk about matrix exponentials and how to find them. And we're going to use them to write down formulas, explicit formulas, for the solutions to any first-order system of differential equations, x prime equals ax plus f, where a is a constant matrix, and I should say a is always an n by n constant matrix. And the formulas are explicit, they're symbolic. In terms of the kinds of problems we've already been studying, the way we've taught you first is usually quicker, but the symbolic formulas are useful, especially if you have a good software package which can compute these explicit formulas, and pretty much every good software package does. Even Wolfram Alpha will compute. I don't think it'll do these formulas, but Wolfram Alpha will compute matrix exponentials. All right, and at the start of Chapter 3, or at the start of Chapters 4 and 5, when we spent all this time emphasizing finding the homogeneous solution space, finding a particular solution, and then getting the general solution, and we kind of guessed what forms these things should take, and I justified that by saying there weren't explicit formulas, as in Chapter 1, for first-order scalar linear differential equations. I wasn't telling you the complete truth. All right, now matrix exponentials are defined for every square matrix, regardless of whether the matrix is diagonalizable or not. As you might expect for diagonalizable matrices, they'll be easier to find. Okay, well, if you were thinking about how to define e to the a, one possible, and probably the only thing you could think of, would be, let's just use the same power series that we used for e to the t. And we can either use it for e to a constant matrix, or for a matrix-valued function, e to the ta. So this is an infinite series. we're not going to worry too much about convergence in this course, but we should at least check that the series, this first series, converges. So let's think about why that's true. So let M be the largest absolute value of all the entries in the matrix. Then when you do A squared, it's a row of A dot a column of A, and the largest absolute value for each one of those individual products is M squared, and you have n of them. So the largest absolute value for any entry of A squared is n times M squared. Then if you take A squared times A to get A cubed, then the largest absolute values of each term there is nm squared times m, and you're adding up n of them, so you get n squared m cubed as the largest absolute value of any entry in A squared, and so on. And so if you check for absolute convergence of the entry, the ij entry of e to the a, you get these estimates just from the Taylor series for e to the a. And those estimates look pretty much like e to the nm. Actually, if you just multiply all of the terms starting with the second one by n, you get exactly e to the nm. So the series, the infinite series for each entry is absolutely convergent, and so it's convergent. Okay, so that's why the series always converge. Now, let's check properties. It's not always going to be true that e to the ab equals e to the ba, and this is related to the fact that matrix multiplication is not commutative in general. But if ab does equal ba, then e to the a, e to the b equals e to the b, e to the a. So let's see why this is true. And in this computation, we won't worry about convergence, but so we'll operate more formally. So let's just write down what is e to the a, e to the b. So that's the identity plus a plus 1 over 2 factorial a squared, 1 over 3 factorial a cubed, and so on, times the identity plus b plus 1 over 2 factorial b squared plus 1 over 3 factorial b cubed, and so on. Okay, now if these were finite sums, I would just add up all of the products where I took one term from the left and one term from the right. They're infinite sums, but I'll still get all possible the sum of all possible products from the left and from the right, and I'll organize these by increasing powers. So if I take I times I get I. If I look at the terms that just have one total power, I'll get a times I plus I times b, which is a plus b. If I look at the terms that have a total power of 2, I'll factor out the 1 over 2 factorial from the a squared times I term. And then I also get an ab term in the product, but if I put it inside the parentheses, that's a 2ab. And then I'll also get an I times 1 over 2 factorial b squared, And if I put it inside the parentheses, I just have a b squared. So I think it's clear, but what I'm doing is I'm just collecting terms. So the I came from that. The A plus B came from that, and so on. Okay, let's do one more so you see the pattern more clearly. I will factor out a 1 over 3 factorial from the terms which have a total power of 3, and I get an a cubed times I, which is a cubed. I get a 1 over 2 factorial a squared b. So if I take a 3 a squared b inside the parentheses, then dividing by 3 factorial gives me the 1 over 2 factorial. And then I will also get an a b squared over 2 factorial, which inside the parentheses will be a 3 ab squared. And then I'll have a 1 over 3 factorial b cubed, which inside the parentheses is a b cubed. And you can see what's going on here. I'm getting the binomial coefficients in front of the 1 over, in front of the total power of n terms. All right, now as far as what we're trying to check here, you can see that if I did e to the b, e to the a, I get the same expansion but with a and b reversed. And if a b equals ba, then all of those products of some power of a times some power of b can be rewritten as the power of b times the power of a. So if ab equals ba, all terms, all expressions inside the 1 over n factorials are equal. So that checks our first claim. Next claim. If a and b commute, then I have the rule of exponents. E to the a plus b is e to the a, e to the b, or as we checked in number 2, e to the b, e to the a. Well, we almost had that on the previous page. So let's see how come this is true. So let's compute e to the a plus b. It is the identity plus a plus b plus 1 over 2 factorial a plus b squared, which I'll write as a plus b times a plus b, plus 1 over 3 factorial a plus b cubed, which I'll write as a plus b, a plus b, a plus b, and so on. Okay, well, let's expand a plus b times a plus b. So when you use distributive property of multiplication over addition, you'll get a times a plus b plus b times a plus b times b. So that's a squared plus AB plus BA plus B squared. When you do A plus B cubed and you use dPMA over and over again, you will get a pure A cubed from the product of all the firsts. Now let's collect the ones that have A squareds in them. So you could get an A times an A times a B. You could get an A times a B times an A. You could get a B times an A times an A. Now all the ones that have just an A to the first in total, you could have an A times a B times a B. You could have an A, a B times an A times an A. And you could have a B, an A, and a B. And then finally, you could have all B's, which is the B cubed. And etc. All right, now, if AB is BA, then e to the A plus B is the identity plus A plus B plus 1 over 2 factorial A squared plus 2AB, that's using the commutativity, plus B squared plus 1 over 3 factorial A cubed plus, we would get 3 A squared B, we would get 3 AB squared, and we would get B cubed. And here you can see we're getting the binomial coefficients. That show up when you take, say, scalar x plus y to the nth using combination coefficients. All right, well, this expression is exactly the expression that we had for e to the A times e to the B. Okay, so if A and B commute, the rule of exponents works. And in particular, a very special case of that is that for any matrix A, e to the A is always invertible, and its inverse is e to the minus A. And that's because e to the A times e to the minus A is e to the A minus A by what we just did, and that's e to the 0 matrix. And e to the 0 matrix is the identity plus the 0 matrix plus 1 over 2 factorial the 0 matrix squared, etc. And everything except for the identity is the 0 matrix. Okay, so here is an example we're going to spend a lot of time on today. And let's use the power series definition to compute the matrix exponential. It'll turn out in practice that we don't usually use the power series. We use things like diagonalization to compute matrix exponentials. But in this example, and in your homework, the power series works out really nicely. Okay, so e to the ta is the identity plus ta plus 1 over 2 factorial, t squared a squared, and so on. So let's start computing the powers of a. So a squared is a times a, and I get minus 1 in the first entry, 0 in the first off diagonal, 0 in the second off diagonal, and minus 1 in the second entry. I get minus the identity matrix for a squared. So a cubed, which is a times a squared, is just a times minus the identity is minus a. And a to the fourth, which is a squared squared, is minus the identity times minus the identity, is the identity. And then when I do a to the fifth, that'll be a to the fourth times a. So a to the fifth will equal a to the sixth will be a squared, a to the seventh will be a cubed, and a to the eighth will be a to the fourth, etc. And so e to the ta will be, and I will write this out using the 2 by 2 matrices, the identity plus t times 0, 1, minus 1, 0, plus t squared over 2 factorial times minus minus the identity, plus t cubed over 3 factorial times minus a, which is a 0, 1, minus 1, 0, plus t to the fourth over 4 factorial times the identity plus t to the fifth over 5 factorial times a plus t to the sixth over 6 factorial times a squared, which is minus the identity, and so on. Okay, so let's just collect the entries, the terms in every entry. Make this big. Okay, so in the 1, 1 entry, I get a 1, I get no t's, I get minus t squared over 2 factorial, no t cubes, I get a t to the fourth over 4 factorial, I get a minus t to the sixth over 6 factorial, and so on. In the 1, 2 entry, I get a t minus a t cubed over 3 factorial plus a t to the fifth over 5 factorial, and so on. In the 2, 1 entry, it is a minus t plus a t cubed over 3 factorial minus the t to the fifth over 5 factorial, and so on. And in the 2, entry, you're seeing the pattern. I hope you get a 1 minus t squared over 2 factorial plus t to the fourth over 4 factorial. You're going to get the same thing as you got in the 1, entry. And look at this. E to the ta is cos t in the diagonals, sine t in the 1, 2 spot, and minus sine t in the 2, 1 spot. How about that? We recognize that. That is the matrix that rotates negative t radians in the counterclockwise direction. In other words, t radians clockwise. Remember, the rotation matrix for an angle theta was cos theta sine theta, because that's where 1, 0 would be rotated to, and minus sine theta cos theta, because that's where 0, 1 would be rotated to. Okay, we're going to come back to this example after we talk about what matrix exponentials have to do with differential equations, and that is Theorem 1. So e to the ta solves the first order matrix differential equation that its derivative is a times itself. And at t equals 0, we get e to the 0a, which we already saw. It's just the identity, because when you look at the power series, every term after the identity has a t in it, so is 0. Okay. We'll think about it for a second, and we'll see that a is equivalent to b, and then we'll make explicit the connection to solving initial value problems of the sort we've solved before. So let's prove a. Well, we want to take the derivative of e to the ta. E to the ta is the identity plus ta plus 1 over 2 factorial t squared a squared plus the general term is 1 over n factorial t to the n a to the n, and so on. Now, if this was a finite sum, I know that the derivative of the sum is the sum of the derivatives. I'll just say, with analysis, you can justify for the infinite sum interchanging summation and differentiation as well. And when you do that, differentiating term by term, you get the 0 matrix plus derivative of t times a is just 1 times a by the product rule, which implies the constant multiple rule in either factor, plus 2t over 2 is t. The next term would have been 1 over 3 factorial. The derivative of t cubed would have been 3t squared a, which is just t squared over 2 factorial times a. And we'll see that when we do the general term, it's 1 over n factorial. Derivative of t to the n is n t to the n minus 1. And n over n factorial is n over n times n minus 1 factorial. So that's just 1 over n minus 1 factorial. So let's factor, so you can see from the first terms that the powers of a are off by 1 from the powers of t, but that's fixed if we factor an a out on the left. We could have also factored the a out on the right, but for our purposes, it's better to factor it out on the left. Then we get an identity plus a ta plus a t squared over 2 factorial a squared. And the general term, after we factor out one of the a's, will be t to the n minus 1 over n minus 1 factorial a to the n minus 1. And you can see inside the brackets, we've just got the power series for e to the ta. We've just changed our indexing from n to n minus 1. So the derivative of e to the ta is a e to the ta. And so we've checked this. And when t is 0 for the power series, we just get the identity plus a bunch of zeros. So we've checked that. All right, so now let's see what B says. Well, A and B are really different ways of saying the same thing, because if we look at column J of the derivative of e to the ta is a e to the ta. We take the derivative term by term, so the derivative of the matrix is also, we can take the derivative column by column. We would get that the derivative of the jth column of e to the ta, so that's the jth column on the left. Well, to get the jth column on the right, we just take a times the jth column of e to the ta. So if we write the jth column as x of t, it satisfies x prime of t equals ax. And since the jth column of e to the 0a is the identity, sorry, since e to the 0a is the identity, x of 0, if we take x of t to be the jth column of e to the ta, x of 0 will be the jth column of the identity, which is j. Okay, so that shows why A implies B, but if you look at it, it's also showing, actually it's showing the equivalence, that to say the statements for e to the ta is the same as saying the statements in part B for the jth columns. Now what's interesting about B is those initial value problems are of the sort we've already been solving, and we'll come back to that. Okay, and now let's look at C. So here we were checking B. If I look at C, notice that e to the t a times x naught is just a linear combination of the columns of e to the t a. Where the weights are just the coordinates of x naught, the components of the vector x naught. And each column solved the homogeneous system, x prime equals ax. So e to the t a x naught is a solution to the first order system. And at t equals 0, we get x of 0 is the identity matrix times x naught, because e to the 0a is the identity matrix. So that's a nifty way, if you know the matrix exponential, to just write down the solution to the kind of initial value problem that we've been solving for several weeks now. And this looks just like chapter 1, except we've replaced all of our scalars with vectors. So in chapter 1, if we were doing the scalar equation, x prime of t equals kx, that was just an exponential growth equation. The solution, or decay, was x of t equals x naught e to the kt. Well, that corresponds to the matrix exponential solution that we're talking about now, except we put the matrix on the left and the vector x naught on the right, as it has to be. Okay, so let's see. For the running example, since A and B are equivalent, let's just check B, and then let's not bother with C. So let's look at, so the first order system was x prime equals ax, and so that's x1 prime, x2 prime. A times x1, x2, the first entry is just x2, and the second entry is minus x1. All right, so let's look at the first column here. If x1, x2 is cosine t minus sine t, then x1 prime, x2 prime is, derivative of cos is negative sine, derivative of negative sine is negative cos, and for our x1 and x2, that is negative, that is x2, which was negative sine t, and negative x1. And the initial value vector for the first column is cos of 0, which is 1, and negative sine of 0, which is 0. So that's the first column, and if I do the second column, I'll have x1, x2 is sine of t, cosine of t, x1 prime, x2 prime is cos t negative sine t, which is x2 negative x1. And when I do the initial value vector, I get sine of 0, which is 0, and cosine of 0, which is 1. Okay, so what we were checking was that when you look at the columns of e to the ta, they solve the initial value problems. X prime equals ax, and x of 0 is, for the jth column, is the standard basis vector, ej. All right, so there's, related to our formula, you can talk about the flow generated by the vector field, at x, which is ax. So here the vector field, and I used xv instead of x1, x2 in this picture, because this first order system actually comes from an undamped spring. So because A was the given matrix, this is the vector field at xv is v minus x. And we've studied this field before. That is the vector field which is tangent to circles centered at the origin. It's perpendicular to the position vector xv. And so if I think of this formula for the solutions to the first order systems that start at x naught, I can think of all of them at once. So all of the x naughts at once. And in other words, I'm thinking of all of R2. And then as t increases, R2 is flowing. It's getting rotated because e to the ta x naught is just this rotation matrix times x naught, and the angle of rotation is t in the clockwise direction. And so all of R2 is flowing tangent to this vector field. And so what this formula did is it let us integrate the tangent field to find where you would be at time t if you started at x naught. So that's what this p-plane picture is illustrating. I didn't use the formula. The formula tells us analytically what's happening. I just used I'd let p-plane plot the numerical solutions. So R2 is getting rotated by this flow. And flows come up in a lot of places, certainly fluid flow, for example. But anytime you have vector fields, you can look at the flows that they generate, and they come up in pure and applied mathematics. So a starting point might be the Wikipedia page, vector flow. Okay. Now, I think I already said this, but I highlighted it on a separate page. Here I've just repeated Theorem 1, so there's nothing new there. I just wanted to refer to it in this remark. So I showed you with power series, that was the definition of e to the ta, and that's one way to compute it. But if you look at 1b, another way to compute it would be to use Chapter 5 I'm trying to remember which section it was. I think it was 5.2, where we talked about the e to the lambda TV methods for solving first-order systems. So you could use that material to solve all n initial value problems, x prime equals ax, x of 0 equals ej, and those would make the columns of e to the ta. Okay, that's not the best way to do it. Well, we actually kind of are thinking of going in the reverse direction. Okay, and since it wouldn't be the best way of doing it, I won't do it that way. If our first order system came from a higher order differential equation, then actually this column by column method could be used, and you know how much I like to talk about this correspondence. So that system that we've been studying corresponds to the unforced, undamped harmonic oscillator second order differential equation. Let's just take a tiny second to check it. So let's see. Ax is x2 minus x1. If I have a solution to the second order dE, then x prime is x prime x double prime. But because I have a solution to the second order dE, that's x prime minus x. And so that shows that xx prime solves the first order system x1 prime x2 prime equals x2 minus x1. We know the solutions to the second order dE. They are x of t equals c1 cos t plus c2 sine t. If for the IVP x of 0 equals 1, x prime of 0 equals 0, the solution is x of t equals cos t And then if I want to connect to the first order system, x prime of t is the derivative of cos t is negative sine t. And if I want to do the IVP where x of 0 is 0 and x prime of 0 is 1, then x of t is sine t and x prime of t is cosine t. So, putting together the fact that the first order system is equivalent to the second order differential equation, and the fact that the columns of e to the ta are solutions to x prime equals ax, where the initial vectors are the standard basis vectors, I know, with no power series at all, that e to the ta has its first column cos t minus sine t, and its second column sine t cos t. Okay. Now, the main way that you'll be computing e to the ta when you don't have a power series, which looks very good, is you'll be using diagonalization. And so let's build up to that in a sequence of a few steps. If we are lucky enough to have a diagonal matrix, then the exponential e to the td is also a diagonal matrix where in the jth spot where there was a lambda j, there's now an e to the lambda j t. And the key thing we're going to use to check this, which you probably remember from linear algebra, is that if you have two diagonal matrices, then their product is 2. And the II entry of BC is just the product of the II entry of B times the II entry of C. And so it's the same if you take multiple products as well. So if we take powers like d to the n, I'll just get the diagonal matrix where the diagonal entries, let's say k, are just the powers of the diagonal entries of the original diagonal matrix. All right. So let's check Theorem 2. And just for simplicity, let's just do it for a 3 by 3 matrix, but everything is completely general. Okay, so e to the td is the identity plus t times lambda 1, lambda 2, lambda 3. On the diagonal, I'll just put giant zeros to indicate that all of the off-diagonal entries are 0, plus t squared over 2 factorial, lambda 1 squared, lambda 2 squared, lambda 3 squared, all Other guys are 0. One more term. Cubes on the diagonal. Zeros everywhere else. And when you look at this sum, all the off-diagonal entries are 0 in each term, so also in the sum. And when you look at the diagonal entries, for example, the 1, 1 entry, you will see a 1 plus a t lambda 1 plus a 1 over 2 factorial t squared lambda 1 squared plus a 1 over 3 factorial t cubed lambda 1 cubed, and so on. If you look at the 2, 2 entry, I'll write it quickly because you can see it. It's just 1 plus t lambda 2 plus 1 over 2 factorial. I'll rewrite this as a t lambda 2 quantity squared plus 1 over 3 factorial t lambda 2 quantity cubed. And as you can see, that's summing up to e to the t lambda 2. And so in the 3, 3 entry, I'll just get e to the t lambda 3. Everywhere else, we had zeros. And so, as we were trying to show, our final 3 by 3 matrix is the diagonal matrix with the exponentials e to the lambda jt on the diagonals and zeros everywhere else. Okay, well, we've been using diagonalization a fair amount to understand some of our first and second order differential equations in a more linear algebra-y way, and that also is the case for matrix exponential. So let's assume that A is diagonalizable. So that means we have a basis of Rn if all the eigendata is real, or of Cn if some of it's complex. And P will be the, therefore, invertible matrix which has those eigenvectors in the columns. If you look column by column, that means that A times the jth column of P, which is A times Vj, is lambda j Vj. You can rewrite that as AP equals PD, where D is the diagonal matrix of eigenvalues. And solving for A by multiplying by P inverse on the right, we get A is PD, P inverse. And that lets us find e to the ta by first computing e to the td and then multiplying on the left using the Theorem Two, and then multiplying on the left by p and on the right by p inverse. So let's check why this is true. Well, e to the ta is the identity plus ta, and a is p d p inverse plus t squared over 2 factorial a squared, which is p d p inverse P d P inverse. I'll write one more term this way, just to hammer home what we're doing here. So PD P inverse, PD P inverse, PD P inverse. The general term is t to the n over n factorial a to the n. May as well write it as PD P inverse to the n. Now, you've probably seen this sort of telescoping behavior in linear algebra. In these products of PD P inverse, the interior P inverse P's all multiply to be the identity. And so you can just kind of erase them from your expansion. And so what you get for e to the ta is the identity. Actually, yeah, okay, that's plus t pd p inverse plus t squared over 2 factorial. Now you get a p. Because the P inverse P got erased, you just get a D squared P inverse plus T cubed over 3 factorial P. If you look at the A cubed, two identities, you just erase them, you get P D cubed P inverse. In general, T to the n over n factorial P D to the n P inverse. And you can factor out a P on the left of everything and a P inverse on the right of everything. And then if you just put an I here, you'll end up with the I that we need. And then on the second term, all that will be left will be a TD. On the third term, all that will be left will be a t squared over 2 factorial d squared. On the nth term, all that will be left will be a t to the n over n factorial diagonal matrix to the n. And the stuff inside the brackets is just e to the td. Which is the nice matrix of the exponentials of the lambda jt. Okay. Yeah, so this is a fun exercise. I meant to have it filled in before I made the video, but it's in our post notes. So you could actually check this. Let me just write out what you'd be checking. So for our running example, the eigenvalues are plus or minus I. You can take eigenvectors to be 1 plus or minus I. So e to the ta would be, so the P matrix could be taken to be 1I. That's the lambda equals I eigenvector. 1 minus I is the lambda equals minus I eigenvector. E The first lambda is plus I. The second eigenvalue is minus I. So these are the e to the lambda I t's. And then the inverse of p using, I won't write it down, you just use the adjugate formula. So I'll just write 1I. 1 minus I inverse. So if you want, you can do this. Okay, now one last comment. So in this remark, I just wrote out more explicitly what e to the t a was. So P was the matrix of eigenvectors. E to the td was the matrix of exponentials of the eigenvalues, the diagonal matrix. Now if you multiply these first two matrices together, you'll see that the first column of the product is just e to the lambda 1 t times v1 plus no v2s plus no v3s and so on, using linear combination expression for matrix times vector. So the first column is e to the lambda 1 t v1. The second column of the product is no v1s plus e to the lambda 2t of the v2s plus nothing else, and so on. So the product of the first two matrices gives us our old friend, the Wronskian matrix for the first order system, x prime equals ax, where we were, in this case, it was the Wronskian matrix of a basis of the solution space because we had a diagonal matrix. So the terminology the text uses in this section is a fundamental matrix solution. So we call a matrix 5T a fundamental matrix solution for x prime equals ax if the columns solve the system and they're a basis for the solution space. So, and this definition works regardless of whether you have a diagonalizable matrix or not. So if you have any first order system x prime equals ax, then phi of t is a fundamental matrix solution if and only if phi prime equals a phi. So that means the column, when you look column by column, that means that the columns of phi solve x prime equals ax. And furthermore, the columns have to be a basis for the solution space. Okay, so that's the general notion of a fundamental matrix solution, which would apply, for example, even if A wasn't diagonalizable. I'm thinking I'll do an example in a separate video of a non-diagonalizable matrix. All right, and just as is the case for the diagonalizable matrix, it's always true that if you start with an arbitrary phi of t, then you can recover the exponential by multiplying on the right by phi of 0 inverse. And so let's just check why that's true. So basically what we did by multiplying on the right by phi of 0 inverse is we just changed our basis of the homogeneous solution space. Let's just compute, let's verify conditions 1 and 2 for this new alleged fundamental matrix solution. So if I take d by dt of phi of t, phi of 0 inverse, then by the product rule, and the fact that one of the factors is a constant matrix, I'll just get phi prime of t, phi of 0 inverse. But phi prime of t was a phi. Multiplication is associative, so I can rewrite this as a times phi of t, phi of 0 inverse. And so that checks condition 1 for this new alleged fundamental matrix solution. And and to show that the new columns are still a basis, it suffices to actually check what happens at the identity. So at t equals 0, phi of t, phi of 0 inverse is just phi of 0 inverse is the identity. So actually, that checks condition 2, and it also shows that phi of t, phi of 0 inverse is e to the ta, because we just checked that the columns solve the system, because the whole matrix solves the system, and the value at the identity at t equals 0 is the identity matrix, and that was how we characterized e to the ta as well. Okay, so this method will work for diagonalizable and non-diagonalizable matrices, assuming you can find a fundamental matrix solution. All right, so the upshot of what we did today is we defined this strange thing called a matrix exponential for any square matrix of any dimensions using power series, using the power series for e to the x, we saw, so we connected e to the ta to differential equations because we saw that the solution to the initial value problem, x prime of t equals ax, x of 0 equals x naught, is e to the ta times x naught. And that generalizes what we did in chapter 1. And then finally, we discussed several ways to compute e to the ta Okay, that is it.